Hello, and welcome to the Sleepy Curiosity channel. As you find a comfortable position, let your body begin to release the weight of the day. If this gentle journey is already starting to slow your thoughts, consider subscribing now, so these stories can keep finding you night after night. Now, let the relaxation settle into your breathing. You exist because, almost 14 billion years ago, there was an imbalance of 1 part in a billion. A tiny asymmetry between matter and antimatter that, had it not existed, would have left the entire universe empty of everything except light. Every star that ever shone, every planet that ever turned, every thought that was ever thought, is the remnant of that almost imperceptible imbalance. And the more we observe the universe, the more remarkable that becomes. There's a question that seems to have an obvious answer, but has challenged physicists for decades. What existed before the universe? The difficulty isn't a lack of theories. It's the fact that the question itself may not make sense. Time, as we know it, appears to have emerged alongside the universe. Asking what came before would be like asking what exists north of the North Pole. That direction simply doesn't exist at that point. What current physics suggests is that there was no before in the conventional sense. The Big Bang wasn't an explosion inside an already existing space. It was the beginning of space itself, of time itself, and of all the energy that would go on to form everything that exists. There was no empty stage waiting. The stage came into being along with the play. And that idea, simple to say, is extraordinarily difficult to absorb. Because all of our intuition about before assumes a time that already exists. But here, time itself wasn't there yet. This isn't just a philosophical problem. It's a direct consequence of Einstein's equations of general relativity. When you apply those equations to the entire universe and trace back through time, you arrive at a point where density and temperature become infinite, what physicists call a singularity. It's the limit of what current physics can describe. What lies beyond that point remains, for now, beyond the reach of science. Not for lack of effort, but because the very tools we use to ask questions stop working at that threshold. And there's a detail that changes everything about this idea. The singularity isn't an explanation, it's a confession. It's physics saying, this is as far as I go. What lies beyond that moment, we still don't know. The Big Bang is often imagined as a massive explosion, a fireball expanding into an empty space around it. But that picture is wrong in a pretty fundamental way. There was no around. There was no external space for the universe to expand into. What happened was different. Space itself began to exist and to expand from within itself. It's an idea the mind resists accepting, because all of our experience of expansion assumes something expanding inside something larger. In the first instance, inconceivable fractions of a second, like 10 to the power of -43 seconds, the entire universe was compressed into a region smaller than anything we can measure. Temperature and density were so extreme that none of the forces we know today existed separately. Gravity, electromagnetism, the strong and weak nuclear forces were probably all one thing, a unified force we still don't know how to describe completely. As space expanded, that energy spread out and cooled. And it was that cooling that allowed things to begin organizing themselves. Not from nothing, but from a soup of pure energy that, as it cooled, condensed into the first particles of matter. It's like water vapor that, as it cools, first forms droplets and then ice, each transition creating a structure that didn't exist before. And each structure opening up possibilities that were previously impossible. In the first milliseconds after the Big Bang, the universe was so hot that matter as we know it couldn't exist. What there was instead was a dense plasma of fundamental particles called quarks and gluons, the building blocks that make up protons and neutrons, but which at that moment still couldn't bind together. The temperature was too high for any bond to hold. It was a universe where the pieces existed, but the game hadn't started yet. As the universe cooled, and this happened very quickly, in a matter of microseconds, quarks combined for the first time and formed protons and neutrons. That moment has a technical name, the quark-hadron phase transition. It's one of the most important events in the history of the cosmos, because it was when nuclear matter began to truly exist. It was the first moment in which something we could call an ingredient of reality took shape. What makes this process even more fascinating is that it was chaotic and symmetric at the same time. For every billion particles of antimatter formed, 1,000,000,001 particles of matter were created, a tiny difference of just one part in a billion. Matter and antimatter destroyed each other almost completely. What was left from that minuscule fraction is everything that exists today, every star, every planet, every atom in your body. The entire visible universe is the remnant of an almost imperceptible imbalance. This shouldn't have happened with such precision, but it did. About 3 minutes after the Big Bang, something remarkable happened. The universe had cooled enough for protons and neutrons to begin fusing and forming the first atomic nuclei. This process lasted only a few minutes, perhaps between 3 and 20 minutes after the beginning, and is known as primordial nucleosynthesis. In a window of time you could live through in a single morning, the universe defined its fundamental chemical composition. During that brief interval, virtually all the helium, lithium, and deuterium nuclei that exist in the universe today were formed. The result was an almost universal chemical composition, approximately 75% hydrogen and 25% helium by mass. Everything else on the periodic table, carbon, oxygen, iron, gold, didn't exist yet. The newborn universe was chemically very simple. And that initial simplicity can still be measured today in the oldest, most untouched regions of the cosmos, like a signature the universe left of itself in childhood. What almost no one realizes is that this primordial composition, that specific mixture of hydrogen and helium, was the necessary condition for stars to exist. And stars were the necessary condition for all other elements to be created. The simplicity of the young universe wasn't a limitation, it was the starting point of a complexity that would take billions of years to unfold. For more than 370,000 years after the Big Bang, the universe was completely opaque. There was no darkness in the sense we know. There was light in abundance, but it couldn't travel. The entire universe was a plasma so dense that photons, the particles of light, were constantly absorbed and re-emitted, unable to travel any significant distance. It was like trying to see inside a star. Light everywhere, and at the same time, a total impossibility of seeing. Then, around 380,000 years after the beginning, the temperature dropped enough for electrons, which until then had been wandering free, to bind to atomic nuclei. That moment is called recombination. With the electrons captured, the plasma that had been blocking light dissipated, and for the first time photons could travel freely through space. The universe became transparent, and the light that had been trapped for hundreds of thousands of years was finally released, in every direction at once. That light still exists. It has traveled for 13.8 billion years and permeates the entire universe in the form of cosmic microwave background radiation, detectable in every direction in the sky. When it was accidentally discovered in 1965 by physicists Arno Penzias and Robert Wilson, they initially thought the signal was interference from pigeons on the equipment. What they had found was the luminous echo of the universe's own birth, and the discovery earned them the Nobel Prize in Physics. One of the greatest scientific findings in history, revealed by pigeons that kept insisting on landing on the wrong antenna. After recombination, the universe entered a period that cosmologists call, with an unusual poetic precision for science, the Dark Ages. The universe was transparent for the first time, but there was nothing to illuminate it. The first stars didn't exist yet. Space was filled with clouds of hydrogen and helium slowly spreading out, with no light source anywhere. It was a vast and silent universe, full of matter, waiting. That period lasted between 150 and 800 million years after the Big Bang. It's one of the hardest eras to study because, without light, there isn't much to detect. Modern telescopes were built, in part, to try to see the end of that era, the moment when the first stars lit up and began to reionize the surrounding gas, like islands of light appearing one by one in a dark ocean. What we know is that the first stars were very different from the ones that exist today. Made almost entirely of hydrogen and helium, since no other element existed yet, they were colossal, potentially hundreds or even 1,000 times the mass of the Sun. They lived briefly, exploded violently, and in doing so scattered the first heavy elements ever produced in the universe into space. They were the ones that began chemically enriching the cosmos. Each explosion was a gift, the ingredients of everything that would come after, dispersed through space, waiting to be gathered. This starts to get more interesting when we realize what was happening on a larger scale. While the first stars were lighting up and exploding, clouds of primordial gas were being shaped by gravity into ever larger structures. The first proto-galaxies were forming, irregular and chaotic clumps of gas and young stars, very different from the elegant spiral galaxies we know today. The universe was learning to organize itself. One of the most puzzling questions in modern cosmology is the problem of matter and antimatter. Physics predicts that, at the moment of the Big Bang, equal amounts of matter and antimatter should have been produced. And when matter meets antimatter, they annihilate each other, producing pure energy. If that symmetry were perfect, the universe would be nothing but a sea of radiation, no stars, no planets, nothing. The fact that we exist is direct evidence that something broke that symmetry. For every billion pairs that destroyed each other, there was a single excess proton of matter. That tiny imbalance, technically called CP violation, is the reason the material universe exists. But why that imbalance occurred is one of the unanswered questions of particle physics. Experiments at the world's largest accelerators have confirmed that the asymmetry exists, but the measured amount isn't enough to explain all the excess matter we see. Something more happened in the first instance of the universe, and we still don't know what. In the first fractions of a second of its existence, the universe went through a period of absurdly accelerated expansion called cosmic inflation. During inflation, which would have lasted somewhere around 10 to the power of -36 to 10 to the power of -32 seconds, the universe grew by a factor of at least 10 to the power of 26. To put that in perspective, it would be the equivalent of a grain of sand expanding into a sphere larger than the current observable universe. All of this in an interval of time that human language doesn't have adequate words to describe. Inflation explains several problems that cosmology without it couldn't resolve, like why the universe is so uniform in every direction, and why its geometry appears so close to flat. But it did something more. It stretched tiny quantum fluctuations to macroscopic scales, forming the seeds of future galaxies. The irregularities we see in the cosmic microwave background are the echo of those fluctuations. In other words, the largest structure of the visible universe has its seed in quantum phenomena that occurred at scales smaller than a proton. The enormous was born from the infinitely small. There's an important difference between the universe and the observable universe, and it says a lot about the limits of what we can know. The observable universe is the region from which light has had enough time to reach us since the Big Bang. Its radius is approximately 46 billion light-years in every direction, not 13.8 billion, as one might expect, because space itself expanded during the time the light was traveling. Beyond that horizon, there may be much more universe, possibly infinite. But that region is, by definition, inaccessible to any observation. No information from there can reach us. From the perspective of a civilization located beyond our observable horizon, we are also invisible. Every point in the universe has its own observable horizon. The cosmos may be far larger than any individual observer will ever be able to see, and science, by definition, can only work with what is observable. What lies beyond is real, but permanently out of reach. In 1929, astronomer Edwin Hubble published an observation that would forever change the way we understand the universe. Distant galaxies are moving away from us, and the farther away they are, the faster they recede. This wasn't an anomaly, it was a law. The universe was expanding. The expansion of the universe doesn't mean that galaxies are moving through space like rockets fired outward. What's expanding is space itself between them. It's like dots drawn on a balloon being inflated. The dots don't move across the surface of the balloon, but the distance between them increases as the balloon grows. No point is the center of the expansion. All points move away from all other points simultaneously. And that's exactly what Hubble showed, not just that the universe expands, but that it expands in a specific way that makes sense if we look back in time toward a single point of origin. In 1998, two independent teams of astronomers were measuring the rate of expansion of the universe using distant supernovas as cosmic rulers. The expectation was to find an expansion gradually slowing down. After all, the gravity of all the matter in the universe should have been putting the brakes on the process. What they found was the opposite. The expansion is accelerating. The universe is expanding faster and faster. That discovery was so unsettling that the scientists themselves took some time to accept it. To explain it, physicists introduced the concept of dark energy, a form of energy that permeates space and acts like a repulsive pressure, opposite to gravity. It doesn't dilute as the universe expands. On the contrary, as space grows, there's more dark energy. And the more there is, the faster space expands. A cycle with no end in sight. What makes dark energy especially troubling is its completely unknown nature. It represents approximately 68% of all the energy in the universe, but it doesn't emit light, doesn't interact with matter in any detectable way, and has never been directly observed in any experiment. Its existence is inferred purely from its gravitational effects on a cosmological scale. The discovery earned the 2011 Nobel Prize in Physics, but the fundamental question, what is dark energy, remains unanswered. It's the most present thing in the universe that has never been directly seen. And there's a detail that changes everything when we think about dark energy. The greatest disagreement between theory and observation in the entire history of physics arises precisely here. The energy of the quantum vacuum, the most natural candidate for dark energy, produces a prediction that is wrong by a factor of 10 to the power of 120. The number 1 followed by 120 zeros. That's the largest known quantitative prediction error in science. Something is deeply wrong in our understanding, and we don't know what. Space-time is one of the most fundamental concepts in modern physics. Einstein proposed, in general relativity, that space and time aren't separate entities, they're dimensions of a single four-dimensional structure. And that structure isn't rigid, it can curve, stretch, and ripple in response to the presence of mass and energy. The most intuitive way to imagine this is the fabric analogy. Picture an elastic surface stretched out, and place a heavy ball in the center. The fabric curves around the ball. Other objects that come close follow the contour of that curve, and what appears to be an attractive force is actually the result of objects following the straightest possible path through curved space. That's gravity according to Einstein, not a force, but a curvature of geometry. An idea that, when it was proposed, seemed too abstract to be real. And that later turned out to be too precise to be just a theory. The most spectacular experimental confirmation of that idea came in 1919, when Arthur Eddington measured the bending of light from distant stars passing near the Sun during an eclipse. The light curved exactly as Einstein had predicted. Since then, the effect has been confirmed countless times with increasing precision, and today it's so well established that GPS systems need to correct for the effect of space-time curvature to function accurately. Every time you use a map on your phone, Einstein's general relativity is working silently in the background. There's a limit to what we can see in the universe, and it's not determined only by distance, it's determined by time. Because light has a finite speed, when observing distant objects we're always seeing how they were in the past, not how they are now. An object a billion light-years away is seen as it was a billion years ago. Astronomical observation is, fundamentally, a journey through time. The most distant objects ever observed, certain galaxies and quasars, exist more than 13 billion light-years away, and we see them as they were when the universe was less than a billion years old. We don't know what they look like today. In many cases they've probably long since ceased to exist in the same form. We're looking at luminous ghosts of a past that no longer exists. And the most unsettling part, the universe we see around us is a composition of different eras all at once, nearby objects seen almost in the present, distant objects seen in their infancy. The speed of light, approximately 300,000 kilometers per second, is often described as the universe's maximum speed limit. And it is, in fact, a limit for any object with mass or any information that needs to be transmitted. But there's something in the universe that moves faster than light without violating any physical law, space itself. Regions sufficiently distant from us are moving away at superluminal speeds, above the speed of light. This isn't a violation of relativity because it isn't matter or information moving through space, it's space itself expanding. Relativity prohibits objects from moving through space faster than light, but places no limit on the rate at which space itself can grow. A subtle distinction, but with enormous consequences. The universe isn't distributed uniformly through space. If we look at sufficiently large scales, we see a structure that no earlier model had predicted, a three-dimensional network of matter filaments separated by enormous voids, which cosmologists call the cosmic web. The filaments are structures made of dark matter and gas, and galaxies are concentrated along them. At the points where filaments intersect, galaxy clusters form, the largest gravitationally bound structures in the universe. Between the filaments exist cosmic voids, regions almost completely devoid of galaxies that can stretch for hundreds of millions of light-years. The largest known void, the Boötes void, is about 330 million light-years in diameter. To put that in perspective, the Milky Way is about 100 to 200,000 light-years in diameter. That void could contain thousands of galaxies like ours, and it's almost completely empty. A cosmic silence of unimaginable proportions. What makes this structure even more remarkable is its origin. The filaments and voids we see today are the direct result of the small density fluctuations that existed in the primordial universe, the same irregularities that cosmic inflation stretched from quantum fluctuations. In other words, the largest structure of the visible universe has its seed in phenomena that occurred at subatomic scales, in the very first instance of the cosmos. The grand map of reality was drawn at a microscopic scale. Everything we've ever seen, measured, touched, or detected, stars, planets, gases, dust, light, you and me, it represents only 5% of the total contents of the cosmos. The rest is made up of dark matter and dark energy, two things we still don't know how to describe in fundamental terms. The physics we've learned, all of chemistry, all of biology, all of observational astronomy, deals with an absolute minority of the universe. Within that 5%, the distribution is surprising. Most baryonic matter isn't in stars or planets, it's in the form of diffuse gas spread between galaxies. Stars represent less than 10% of all baryonic matter. Rocky planets like Earth are an even smaller fraction, a rarity within a rarity. What this means is that the human experience of solid, tangible, structured matter is deeply atypical in relation to the universe as a whole. The most common condition of matter in the cosmos is to be a thin, hot gas floating in intergalactic space. The solidity we feel when touching a table is, on a cosmic scale, a pretty uncommon exception. The atom is often described as the fundamental building block of matter, and while that description is useful, it hides a much stranger reality. If an atom were magnified to the size of a cathedral, its nucleus would be smaller than a grain of sand at the center of that space. The rest would be empty, occupied by the wave functions of electrons, regions of probability where electrons can be found, but not fixed trajectories. This means that solid matter, as we know it, is almost entirely empty space. The sense of solidity we have when touching an object doesn't come from contact between dense particles, but from the electromagnetic repulsion between the electron clouds of atoms. When you rest your hand on a table, the electrons in your hand and the electrons in the table repel each other, and it's that force that keeps your hand from passing through the surface. Solidity isn't presence. It's an invisible barrier of force. The atomic nucleus itself is incredibly dense. 1 cubic centimeter of pure nuclear material would have a mass of about 200 million tons. That's the kind of density found in neutron stars, the densest objects in the universe that haven't completely collapsed into black holes. Matter as we know it is, fundamentally, almost nothing, structured by forces that hold that almost nothing together in an extraordinarily stable way. Protons and neutrons are made of quarks, particles that, as far as we know, have no internal structure and are truly fundamental. Quarks are never found in isolation in nature. The force that holds them together has a strange property, unlike gravity and electromagnetism, which weaken with distance. The force between quarks increases as they move apart. It's like a spring that gets more tense the more it's stretched. If you try to separate two quarks, the energy required to do so becomes sufficient to create a new pair of quarks, and the result is 2 hadrons instead of 1, not free quarks. This phenomenon, called color confinement, means that individual quarks exist only inside composite particles and never in free space. The only known exception is the quark-gluon plasma that existed in the first microseconds after the Big Bang, and that was briefly recreated in particle accelerators. The most primitive condition of the universe, recreated for a fraction of a second inside a human-made machine. There's a particle that passes through your body in astronomical quantities at this very moment, without you noticing anything at all, the neutrino. Every second, approximately 65 billion neutrinos produced by the Sun pass through every square centimeter of your hand, and virtually none of them interact with any atom in your body. They pass through the entire Earth as if it were almost completely transparent. To have a 50% chance of stopping a single solar neutrino, you'd need a block of lead about 1 light-year thick. They're almost ghost-like particles, existing in 3 flavors and possessing the strange ability to oscillate between those flavors as they travel, which demonstrates that they have mass, though an extraordinarily small one. In a detector the size of a building, only a few neutrinos interact per day. Even so, those few events are enough to learn about the interior of the Sun, about distant supernovas, and about the fundamental properties of matter. One of the most fundamental questions in particle physics is why particles have mass. The solution proposed in the 1960s, that there exists a field permeating all of space, and particles acquire mass through interaction with that field, became known by the particle associated with it, the Higgs boson. For decades, it was the missing piece of the Standard Model, theoretically predicted, but never observed. The search for it was one of the main reasons for building the Large Hadron Collider at CERN, the largest and most complex scientific instrument ever built, with 27 kilometers of circumference beneath the Franco-Swiss border. In July 2012, after decades of searching and billions of euros invested, the discovery was announced, and Peter Higgs, then 83 years old, was present in the room when the result was revealed. The Higgs field is everywhere, all the time. Every particle with mass is constantly interacting with it. Without it, particles would have no mass, wouldn't form atoms, and the universe would be a sea of structureless particles traveling at the speed of light in every direction. If you look at a spiral galaxy and try to calculate its mass from the light it emits, you'll arrive at a number. Then, if you measure the speed at which the stars at the edges of that galaxy orbit its center, you can calculate the mass needed to keep those stars in orbit. The problem is that those two numbers don't match. The orbital speed of stars at the edges is far too high to be explained by the visible mass. There's missing matter, a lot of it. This discrepancy was first observed with rigor by astronomer Vera Rubin in the 1970s, while studying the Andromeda galaxy. She expected to find stars at the edges orbiting more slowly than those at the center, just as the outer planets of the solar system orbit more slowly than the inner ones. But the rotation curves were essentially flat. The only consistent explanation is that galaxies are immersed in halos of invisible matter, matter that has mass and therefore exerts gravity, but that doesn't emit, absorb, or reflect light in any detectable way. That's dark matter. Dark matter isn't just an anomaly in individual galaxies, it's a fundamental structural component of the entire cosmos. It represents about 27% of the total content of the universe, more than 5 times the amount of ordinary matter. In galaxies, it's distributed in spherical halos that extend far beyond the visible edges. In the Milky Way, the dark matter halo is estimated to be at least 10 times the mass of all the galaxy's visible matter combined. It's the invisible framework upon which all galactic structure was built. Without it, galaxies wouldn't exist the way they do. One of the most elegant pieces of evidence for dark matter is the Bullet cluster, 2 galaxy clusters that collided. The collision physically separated the visible hot gas from the galaxies and their associated dark matter. The gas, which interacts electromagnetically, was slowed by the collision and remained in the middle. The dark matter, which interacts only gravitationally, passed through the collision almost unaffected and continued forward. Gravitational lensing clearly showed 2 concentrations of mass separated from the gas, exactly where the dark matter should have been. It was one of the most direct demonstrations that dark matter exists and is distinct from ordinary matter. the invisible object revealing its presence through the distortion it causes in the space around it. A star is born from collapse. Somewhere in a cloud of interstellar gas and dust, cold, dense, and dark, some disturbance initiates a process that can't be reversed. Gravity begins pulling the gas inward, and the cloud starts to collapse in on itself. As the gas falls toward the center, it heats up. Gravitational energy converts into thermal energy. The forming core, called a protostar, doesn't yet fuse hydrogen, it shines only from the heat of collapse. The decisive moment arrives when the temperature at the core reaches about 10 million degrees Celsius. At that point, protons, hydrogen nuclei, have enough energy to overcome the electrical repulsion between them and fuse. Nuclear fusion begins, releasing an enormous amount of energy. That energy creates an outward pressure that counterbalances gravity. The collapse stops. The star is born. And the balance between gravity and radiation pressure is what will define it for the next millions or billions of years. The Sun is a median star, neither exceptionally large nor small, and that makes it an extraordinarily useful scientific object. Every second, the Sun converts about 600 million tons of hydrogen into helium. In that process, approximately 4 million tons of mass are converted directly into energy. That energy is produced in the core and takes a surprisingly long time to reach the surface. Estimates point to somewhere between 10,000 and 170,000 years, because photons are constantly absorbed and re-emitted by particles in the solar interior in a random unwinding path. The light warming your skin today may have been produced in the core of the Sun long before any human civilization existed. It traveled for millennia inside the Sun before finally escaping and covering the 150 million kilometers to Earth in just 8 minutes. The Sun has enough fuel to continue that process for another 5 billion years, roughly the same amount of time that has already passed since its formation. A stability that's almost incomprehensible in human terms. The mass of a star is the most important parameter of its existence. It determines temperature, brightness, color, lifespan, and, decisively, the way the star will die. Massive stars live fast and violent lives. Low-mass stars live for hundreds of billions of years in an almost monotonous stability. A star with 25 solar masses may live only 7 million years. The Sun will live about 10 billion years in total. A red dwarf with half the mass of the Sun can burn hydrogen for 50 to 100 billion years, far longer than the current age of the universe. The most common stars in the universe are red dwarfs, which represent about 75% of all stars in the Milky Way. If planets around red dwarfs can support life, they would have immensely larger timescales available for evolution, orders of magnitude greater than what life on Earth has had. The universe may only just be beginning to explore the possibilities of complexity. All elements heavier than hydrogen and helium were created inside stars, and that statement has an implication that goes beyond chemistry. Every carbon atom in your body, every oxygen atom you breathe, every iron atom in your blood was forged inside a star that existed before the sun and exploded at the end of its life, scattering those elements into space. You are, literally, made of the remnants of dead stars. Nuclear fusion in stars progresses toward increasingly heavier elements as previous fuel runs out. That process has a natural limit: iron. Iron is the element with the most stable nucleus of all. It's the point where nuclear fusion stops releasing energy and starts consuming it. When the core of a massive star accumulates enough iron, fusion stops and the pressure that had been holding the star up against gravity disappears in fractions of a second. The collapse is almost instantaneous, and the explosion that follows, the supernova, is intense enough to forge all elements heavier than iron, from cobalt to uranium, in a matter of seconds. In 2017, the LIGO gravitational wave detector captured the signal of two neutron stars colliding 130 million light-years away. Analysis of the light emitted by the merger revealed the spectral signature of heavy elements being created in real time. Estimates indicate that the event produced quantities of gold and platinum exceeding the mass of several planets combined. In a matter of days, the fusion of two compact stars had synthesized more precious metals than the Sun will ever produce in its entire existence. This suggests that most of the gold and platinum in the universe, including what's on Earth and in every piece of human jewelry, was created in neutron star mergers. Every gram of gold has a history that traces back to one of the most violent events in the cosmos: two dead stars orbiting each other, spiraling closer for millions of years, until the final collision that released more energy in fractions of a second than most stars release in their entire lifetime. The beauty of a ring has an extraordinarily violent origin. When a star like the Sun exhausts the hydrogen in its core, the star becomes a red giant. Its radius increases by a factor of tens to hundreds. In the Sun's case, it will expand until it engulfs the orbit of Venus and possibly that of Earth. For anything still existing on Earth's surface at that time, it will be the end. Long before being physically swallowed, Earth will have been sterilized by the progressive increase in solar luminosity. What remains at the center of a star like the Sun, after it expels its outer layers, is the exposed core of a white dwarf. It's an object roughly the size of Earth, with the mass of a star, that simply radiates its residual heat into space for billions of years, slowly cooling until it becomes, in theory, a black dwarf. No black dwarf exists yet in the universe, because the process would take longer than the current age of the cosmos. The universe isn't old enough yet to have finished cooling its dead stars. Massive stars don't die quietly. When their nuclear fuel runs out in a cascade of increasingly rapid fusion stages, the core collapses in a matter of seconds. The speed of the collapse is staggering. The core, which is the size of a city, reaches the density of an atomic nucleus in less than a second. The energy released in that instant is greater than the energy emitted by the Sun over its entire 10 billion year lifetime. The shock wave generated by the collapse destroys the outer layers of the star in an explosion called a supernova. For days or weeks, a supernova can shine as brightly as an entire galaxy, billions of stars combined. It's in the seconds of collapse that the heaviest elements on the periodic table are forged: gold, platinum, uranium, lead. A single supernova can produce a quantity of gold greater than the entire mass of Earth. Those elements are scattered through space by the explosion, enriching the interstellar clouds that will give rise to the next generations of stars and planets. Death and creation, in the same instant. There's a point in the collapse of a massive star where known physics simply stops working. When the remaining core after a supernova has enough mass, no known force in nature is capable of halting the gravitational contraction. Matter keeps collapsing indefinitely, until it reaches a density that the equations describe as infinite. The result is a black hole, a region of space where the curvature of space-time becomes so extreme that not even light can escape. The boundary of a black hole isn't a solid surface. It's a purely geometric limit called the event horizon, the point beyond which all possible trajectories in space-time point inward, toward the central singularity. The event horizon is the point where the future becomes only one direction, inward. To an outside observer, an object falling into a black hole never appears to actually cross the horizon. Due to gravitational time dilation, the object appears to progressively slow down and freeze. But from the point of view of the falling object, it crosses the horizon without feeling anything special, and from that point on, the singularity is inevitable. In 2019, the Event Horizon Telescope, a global network of radio telescopes, produced the first direct image of the shadow of a black hole at the center of galaxy M87, 55 million light-years away. What had seemed impossible for decades, photographing something that emits no light, was achieved by turning the entire Earth into an interferometry telescope. The image that appeared on the screen, an orange ring of heated matter surrounding a central darkness, is one of the most extraordinary photographs in the history of science. At the center of nearly every large known galaxy there exists a supermassive black hole, objects with masses ranging from millions to billions of times the mass of the Sun. The black hole at the center of the Milky Way, called Sagittarius A*, has approximately 4 million solar masses and is about 26,000 light-years from Earth. Despite its colossal mass, it's relatively quiet at the moment. But in other galaxies, supermassive black holes in active accretion phases, consuming matter and launching energetic jets, can shine brighter than entire galaxies. Those are quasars. Quasars are the brightest objects in the observable universe. They emit more light than entire galaxies from a region smaller than the solar system. The fact that quasars are observed predominantly at great distances, and therefore in ancient eras of the universe, indicates that this phase of intense activity was more common in the young universe. Nearby galaxies, including the Milky Way, have supermassive black holes at their centers, but relatively quiet ones. The interpretation is that quasars are the young and active phase of the same black holes that today sleep at the centers of galaxies, and that as the universe aged, the available supply of gas diminished, and the monsters gradually fell dormant. Stephen Hawking proposed in 1974 a result that surprised the physics community: black holes aren't completely black. Combining quantum mechanics with general relativity, Hawking showed that the event horizon of a black hole must emit a faint thermal radiation. The implications are profound. If a black hole continuously emits energy, it loses mass over time. A black hole with the mass of the Sun would take approximately 10 to the power of 67 years to evaporate completely, a time astronomically greater than the current age of the universe. But in principle, every black hole eventually disappears. The problem is what happens to the information. According to quantum mechanics, information can never be destroyed. But if a black hole evaporates completely, what happens to the information of everything that fell into it? Hawking radiation, being purely thermal, doesn't appear to carry that information. That conflict, the black hole information paradox, is considered one of the most important theoretical problems in current physics, and remains without a consensus solution. It's the place where two of the greatest theories in human science directly contradict each other, and no one yet knows which one gives way. Neutron stars are objects with densities that simply have no parallel in human experience. With the mass of a star compressed into a sphere only 20 to 30 kilometers in diameter, a teaspoon of their material would have a mass of approximately 1 billion tons. The surface of a neutron star is a solid crust with a hardness that surpasses any known material by about 10 billion times. In the deepest interior of a neutron star, physics enters completely uncharted territory. The densities are so extreme that neutrons may dissolve back into free quarks, forming states of matter that exist nowhere else in the known universe. Neutron stars are, in that sense, the only natural laboratories where that physics can be tested, indirectly, through observations of their size, mass, and orbital behavior. Rapidly rotating neutron stars with intense magnetic fields emit beams of electromagnetic radiation from their magnetic poles. When one of those beams periodically points toward Earth, we detect regular pulses of radio waves or X-rays. These objects are called pulsars. The most stable ones keep a rhythm so regular that it rivals the best atomic clocks built by humans. The first confirmed extrasolar planet was discovered in 1992, not around a common star, but around a pulsar. A planet orbiting a dead star, found through the perfectly regular rhythm of its pulses. Among neutron stars, there exists an even more extreme subclass, magnetars. These are neutron stars with magnetic fields so intense they surpass any other known object in the universe. In December 2004, a magnetar located 50,000 light-years away emitted a flare lasting only 0.2 seconds that visibly disturbed Earth's ionosphere and was detected by virtually every gamma-ray satellite in operation at the time. An event that lasted less than a fifth of a second, and was felt 50,000 light-years away. The scale of violence in the cosmos is rarely so directly demonstrated. Gravitational waves are disturbances in the fabric of space-time that propagate like waves, predicted by Einstein in 1916, but considered by many physicists to be undetectable in practice for a century. In September 2015, the LIGO detectors in the United States captured exactly that signal. Two black holes with masses of 29 and 36 times that of the Sun, orbiting each other in a progressive spiral for billions of years, merged in a fraction of a second. At the moment of the merger, they released more energy in the form of gravitational waves than all the light emitted by all the stars in the observable universe in that same instant. And that colossal event produced a disturbance of less than 1,000th of the diameter of a proton in the terrestrial detectors. The detection opened a new window onto the universe. With gravitational waves, it's possible to observe the merger of black holes, the collapse of stellar cores, and potentially echoes of the Big Bang itself, events that were completely invisible to any conventional telescope. The Milky Way is between 100,000 and 200,000 light-years in diameter, contains between 100 and 400 billion stars, and the Sun is located in a minor arm, about 26,000 light-years from the galactic center. We've never seen the Milky Way from the outside. All of our understanding of its shape has been built indirectly, like trying to draw a map of a forest without ever having left it. The nearest star to the Sun, Proxima Centauri, is 4.2 light-years away, a distance that a probe traveling at the current speed of our spacecraft would take about 70,000 years to cover. Multiplied across hundreds of billions of stars, the Milky Way is almost entirely empty space, a structure of a vastness that no human experience offers any basis for intuitively understanding. The Milky Way is currently in the process of absorbing several smaller satellite galaxies. And the most significant interaction in the near future is the impending collision with the Andromeda Galaxy. Andromeda is approaching at about 110 kilometers per second and is expected to collide with the Milky Way in approximately 4.5 billion years. The result will be a gradual merger that will transform the two spiral galaxies into a single giant elliptical galaxy. What that collision won't be is a crash of stars. Galaxies are so full of empty space that individual stars almost certainly won't collide directly with each other. What will happen instead is a violent gravitational reorganization. The orbits of stars will be radically disrupted, the spiral structures will be destroyed, and waves of star formation will be triggered. The Sun may be ejected into a completely different orbit within the resulting galaxy, but it will probably continue to exist. One of the greatest cosmic collisions in the local history of the universe, and most of the stars won't even notice. The James Webb Space Telescope, launched in 2021 and operational since 2022, is revealing something unsettling for existing models. It has been finding massive and structured galaxies in eras of the universe so ancient that they shouldn't have had time to form, at least according to current models of galactic formation. Galaxies with billions of solar masses existing when the universe was less than 700 million years old are difficult to explain. With each new image from the James Webb, our understanding of the young universe is challenged a little more. The speed of light isn't just a speed limit, it's one of the most fundamental facts about the structure of the universe. It doesn't matter if you're standing still, moving at half the speed of light, or chasing a photon in a hypothetical spacecraft, light will always move away from you at the same speed. Einstein was radical in his answer as to why, because space and time aren't absolute. They deform in different ways for observers in motion, precisely in order to ensure that the speed of light remains constant. That deformation of space and time isn't an illusion or a measurement artifact, it's real physics with measurable consequences. High-energy particles produced by cosmic rays in Earth's upper atmosphere, called muons, should disintegrate before reaching the surface. But they arrive in abundance because, from their perspective, time passes more slowly and distance contracts. Without relativistic time dilation, muons wouldn't exist at ground level. It's an everyday confirmation, albeit an invisible one, that time isn't universal. Gravitational time dilation is equally real. The closer you are to a mass, the more slowly time passes for you compared to someone farther away. The GPS system needs to correct for both the gravitational effect and the effect of the satellite's velocity to provide accurate coordinates. Without those relativistic corrections, the system would accumulate positioning errors of about 10 kilometers per day. Every time you use a map on your phone, Einstein's theory is working silently to make sure the street you see is the street where you actually are. The vacuum of space isn't empty. From the perspective of quantum mechanics, absolutely empty space is impossible. The uncertainty principle prohibits any system from having exactly zero energy. The result is that the vacuum seethes with quantum fluctuations. Pairs of particles and antiparticles spontaneously arise from nothing, exist for a fraction of a second, and annihilate each other. That phenomenon has measurable consequences. The Casimir effect demonstrates that two metal plates placed very close together in a vacuum are slightly attracted to each other by the differential pressure of the fluctuations. The vacuum, absolute nothingness, exerts a force. Gravitational waves aren't the only phenomenon that can, in principle, bring us information from eras before the transparent universe. Primordial neutrinos, produced in the first seconds after the Big Bang, still permeate the universe and could in theory be detected, providing information from an era when the universe was still opaque to light. And background gravitational waves, disturbances produced by inflation itself, would be the oldest signal we could detect, a direct echo of the very first instance of the cosmos. The Hubble tension is one of the most discussed anomalies in observational cosmology. The current rate of expansion of the universe, measured directly from observations of nearby supernovas and Cepheid stars, is systematically higher than what's predicted by the parameters obtained from the microwave background radiation. That discrepancy hasn't gone away with more precise measurements, on the contrary, it has grown. It could be a systematic error not yet identified. But it could also be a signal of new physics, that the early universe and the current universe evolved in ways slightly different from what the standard model predicts. The question remains open. There's a tension at the heart of modern physics that has lasted a century and still hasn't been resolved. The two most well-tested and precise theories science has ever produced, quantum mechanics and general relativity, are fundamentally incompatible. Each one works extraordinarily well in its own domain. Quantum mechanics describes the behavior of subatomic particles with a precision that rivals any other scientific theory. General relativity describes gravity and the structure of spacetime with equally astonishing precision. But when you try to apply both simultaneously, in situations where gravity is intense and scales are quantum, the equations produce nonsense. The central problem is that general relativity describes spacetime as a continuous and smooth structure, while quantum mechanics predicts that at extremely small scales spacetime should be granular, discrete, seething with quantum fluctuations. Unifying these two theories is the central project of modern theoretical physics. The most developed approaches, string theory and loop quantum gravity, haven't yet produced experimentally verifiable predictions. The theory that will unify gravity and quantum mechanics doesn't exist yet, and its absence is the most fundamental gap in our knowledge of the universe. Quantum entanglement is one of the most debated and misunderstood phenomena in modern physics, and also one of the most real and well confirmed. When two particles interact in certain ways, they can become entangled. Their quantum states become correlated such that measuring one particle instantaneously defines the state of the other, regardless of the distance between them. Einstein called this spooky action at a distance and believed it demonstrated an incompleteness in quantum mechanics. Experiments have shown that entanglement is real and that Einstein was wrong on that point. The crucial aspect is that entanglement doesn't allow information to be transmitted faster than light. The correlation only becomes visible when you compare the results of the two measurements through a classical channel, which is limited by the speed of light. Entanglement is non-local, but it doesn't violate causality. And what it implies for the nature of reality is deeply unsettling. It suggests that separation in space isn't absolute from a quantum point of view, that the spatial separation we experience may be an emergent property of a more fundamental structure where the notion of distance doesn't exist in the same way. The Fermi paradox is one of the most puzzling questions that emerges from the combination of astrophysics and biology, given the immeasurable size of the universe, the abundance of stars with potentially habitable planets, and the time available for life and intelligence to develop. Where is everyone? Why does the universe seem so silent? The Milky Way has between 100 and 400 billion stars. Most have planets. Billions of those planets are in habitable zones. The universe is 13.8 billion years old, enough time for civilizations to arise, develop, and colonize the galaxy several times over, even with modest technology. And yet, silence. The proposed solutions are numerous. Perhaps life is far rarer than we imagine. Perhaps intelligent life tends to destroy itself before reaching interstellar scales. Perhaps there exists a filter, an extraordinarily unlikely obstacle in the path of complex life, and the most unsettling question is whether that filter lies in our past or in our future. The ultimate fate of the universe is a question that cosmology can approach with rigor. The most likely scenario, given what we understand today about dark energy, is called the heat death. As the universe continues expanding, the formation of new stars will progressively cease for lack of gas. Existing stars will exhaust their fuel over trillions of years. White dwarfs will cool. Black holes, after unimaginable timescales, will evaporate through Hawking radiation. The timescales involved in that process require a different kind of notation. In about 10 to the power of 14 years, 100 trillion years, the last low-mass star will go dark. In about 10 to the power of 100 years, the largest supermassive black holes will have disappeared. What remains is a universe of isolated particles, photons, neutrinos, electrons, and positrons, separated by distances growing exponentially, in a cold, dark universe in perfect thermodynamic equilibrium. No structure. No process. No information moving anywhere. The universe won't end with an explosion, but with a progressive and absolute silence. The Big Rip is the most dramatic alternative fate. If dark energy isn't constant, if its intensity increases over time, the expansion could progressively accelerate until it overcomes all known forces at ever smaller scales. The progressively accelerating expansion would overcome gravity between galaxies, then between stars, then between planets, then between atoms, and eventually between subatomic particles themselves. The very fabric of matter would be torn apart by the infinite expansion of space. An end that would leave no fragment untouched. The fate of the universe depends entirely on the nature of dark energy, and since we don't know what it is, we can't predict with certainty what will happen. It's one of the most open questions in all of science. The universe that began in a singularity of infinite density will end in infinite expansion or in absolute silence. And we, organisms that exist for the blink of an eye in cosmic history, have managed, with instruments and mathematics, to map that history from beginning to probable end. There's something remarkable about the fact that the universe can be described in mathematical language. The equations of general relativity, quantum mechanics, thermodynamics, all were developed by human beings studying phenomena accessible in earthly laboratories, and yet they work with extraordinary precision at scales ranging from the subatomic to the cosmological, in eras spanning from the first instance after the Big Bang to the present. What's undeniable is that the universe has a deep coherence. The same laws that govern the fall of an apple govern the orbit of planets, the structure of galaxies, and the expansion of the cosmos. The same atoms that make up rocks make up stars and thinking beings. The universe is, in some fundamental sense, a single thing, vast, ancient, strange, and surprisingly intelligible. And the fact that organisms that evolved in a tiny corner of that universe can map its 13.8 billion year history, infer the composition of its 96% invisible content, detect gravitational waves from collisions that occurred billions of light years away, and ask about its beginning and its end, that, in itself, is one of the most extraordinary facts of the cosmos. There's something deeply comforting in that immensity. Not the immensity that crushes, but the immensity that holds. You're made of the same atoms as the oldest stars in the universe. The matter in your body traveled for billions of years and billions of kilometers to organize itself, for a moment, into the shape of someone who can look up at the sky and wonder where it all came from. And as those thoughts settle, as the vastness of the cosmos begins to feel less distant and more close, let the weight of your body deepen, and allow the silence of the universe, the same silence that exists between galaxies, between stars, between atoms, to be also the silence within you. And as you drift into a deep and restful sleep, remember to subscribe, so these stories can keep finding you, night after night. Sleep well, and sweet dreams.